These next tests require cooperation. Consequently, they have never been solved by a human. That's where you come in. You don't know pride. You don't know fear. You don't know anything. You'll be perfect.
Hey, I'm Alex. This video is recorded from my point of view. I'm playing as the blue robot.
And I'm Phil. I'm playing as the orange robot.
Today we're going to be playing through parts of Portal 2 and explaining the laws of physics as they apply to the game.
While we have recorded partial solutions to some of the test chambers, we've been mindful of the fact that some viewers may not have played through Portal 1 or 2 yet, but may want to in the future. This video contains no plot spoilers and shows only partial solutions to a few slip chambers.
During our experiments, you may hear a robotic voice make sarcastic comments in the background. This is GLaDOS. She runs things around here.
Hello, and again, welcome to the Aperture Science Computer-Aided Enrichment Center.
The most important concept in this game is the portal. Portals by themselves are very simple. When something goes into one, it comes out the other, like so.
Portal 2 and its predecessor are both centered around solving puzzles using these portals. In this video, we will be demonstrating how Portal 2 uses and misuses physics. In this chamber, we'll be talking about the fundamental concept of conservation of energy, and how one can use portals to manipulate and bend this rule.
Usually when falling, potential energy, given by mass times gravity times height, is quickly converted by gravity into kinetic energy, given by 1/2 mass times velocity squared. When finally impacting with the ground, this energy is converted into heat, sound, pain, and other forms of energy.
With portals, one can make surprising instantaneous changes to one's location and potential energy. This is achieved by the instant transportation from the blue portal to the purple portal. However, if Phil jumps into the blue portal with no previous energy, he's unable to make the jump into the ledge.
So that means that I need more potential energy to start with. Let me get onto that ledge over there. Now if I jump into the blue portal, gravity will have done work on me. Now I'll come out of the purple portal with more speed.
Kinetic energy, and therefore speed, is conserved between portals, allowing Phil to fly across the chasm and land on the ledge.
However, this seems to violate the law of conservation of energy. How can I suddenly have more potential energy with no change in kinetic energy?
In order to achieve this, with our understanding of physics, the portals must have done work on you, equal to the mass times gravity times change in height. If the last chamber made you angry about how the law of conservation of energy was bent in Portal 2, leave the room now. This next example is much, much worse. Hi Phil, how are you doing? Fine, be that way.
For that, Blue is penalized 50 science collaboration points.
Phil, you're late. Get in the Aperture Science perpetual motion apparatus. We have a video to make.
Hate you. We're gonna cut that out, right?
Nope. As expected, when in free fall, objects, especially people or robots, eventually approach terminal velocity. How does it feel?
Robots feel no pain.
Excellent. Feel like going through some calculations? We start with a free body diagram which shows the object in motion. Since it's accelerating, the sum of the forces is equal to mass times acceleration. There are two forces acting on this body, gravity and drag.
Actually, this is rather disorienting. Could we perhaps leave the calculations to Mr. Jacobs?
Works for me. But for those who are interested, I'll show you quickly. You guys are good at note-taking, right?
For those who didn't quite catch that, allow me to explain. Terminal velocity is reached when the downwards force of weight is negated by the upwards force of drag. This is almost achieved in activities such as skydiving, or by using the Aperture Science perpetual motion apparatus.
And, as we learned from the previous chapter, there is a conservation of speed between portals. This allows me to launch Phil at terminal velocity, as we saw before, into the Aperture Science timed obstacle, or across the pit to the exit.
Actually worked. In this chamber, we touch on the idea of collisions, most specifically perfectly elastic collisions, and painful, also known as inelastic collisions.
Elastic collisions are when two objects, after coming into contact with one another, bounce off each other. In a perfectly elastic scenario, there is no energy or momentum lost during the collision. An example of these collisions would be two billiard balls colliding and bouncing off each other with equal speed in opposite directions.
Inelastic collisions, on the other hand, are collisions in which kinetic energy is not conserved. In a perfectly inelastic collision, the two objects collide and stick together, and their momentum remains the same.
As we can see here, we need to move ourselves to the other side of this pit. However, our only means of transportation is jumping across these two platforms. When jumping onto one of the platforms, an inelastic collision occurs. This is seen when Phil jumps onto his first platform. Most of the kinetic energy gained from gravity is converted into heat and sound.
This means that I don't have nearly enough energy to make the next jump, let alone make it to the exit.
In order to keep that energy, we need to make these collisions elastic.
Hello.
Yay, Orange is back.
As previously seen, it is impossible to navigate this pit by jumping without an elastic surface to land on. In order to combat this, we have coated the platforms with a blue repulsion gel.
This gel makes all surfaces act like elastic surfaces rather than inelastic surfaces. Now that these surfaces are coated with the gel, I can jump from platform to platform with ease.
Notice how Phil comes up to exactly the same height with each jump. When he lands, all of the energy is conserved, so he is able to reach the peak height over and over, rather than losing it to heat or sound.
In this final chamber, we will be talking about momentum and how it is portrayed in Portal 2. In this game, portals do not always conserve momentum. This is seen in the current example, where the momentum is exactly reversed by the portals.
Let's have GLaDOS introduce momentum.
Momentum, a function of mass and velocity, is conserved between portals. In layman's terms, speedy thing goes in, speedy thing comes out.
What she said wasn't entirely true. While the magnitude of a player's momentum is conserved when going through a portal, their momentum vector is almost never conserved. Your momentum changes when you change direction, so even if a player is going the same speed as he was before, if he has changed direction, then he has changed momentum.
That's it from us. Hope you enjoyed this video.